Next speaker is Sara from Google Research.
Hi everyone, I'm going to talk about attacking cardinality sketches. This is a joint work with Billy. So in this talk, I'll talk about how to attack cardinality sketches via doing a single batch attack. So with it's non-adaptive, or doing a quadratic size on any query response algorithm. So I first talk about give you some background on cardinality queries, composable sketches, and such, and then talk about our work and then conclusion. So for cardinality sketches, we actually take a look at F0 frequency moment or L0 known. So we are given a set or a group of items. We might have a repetition. And we basically want to say how many distinct different items I'm seeing. Or you can consider a vector that we have some numbers in it, and then we just want to count the number of non-zeros. And then this has applications in counting, for example, the different users that visited my website or distinct search queries and so on. So let's just giving you some background. I know that some of this is repeated, but just go through it for being complete. So we have a data set D, and then we look at the sketch of this data set. And then the idea is that if I have a function that I want to apply to my data, then I can find some estimator to the sketch that is much smaller. And the idea is that I'm looking for a sketch that is much smaller in size, so I can use efficient storage. And we are also looking for composability problem. So what is being composable? So it's a property that if you have a data A and data B, and then we look at the union of these two data, then it's the sketch of the union can actually be derived from the sketch of the two sets. And why is it useful? Because then we can look at distributed computation. We can distribute our data, do parallel computation. Also, it's good for answering composition queries. For example, what happened on certain combinations of days. And so composable sketches for now, let's go back to our main problem. We have the cardinality estimation problem at hand, and we want composable sketches. Explicit representation of Bloom form data doesn't exactly work. We will have a same order as our data, but there have been a long line of research on this, and there are very efficient sketches that they also have efficient implementations. And then so the sketches the sketch size is log n plus k, where n is our dimension, and then k would be related to our error rate. So for example, for NMSC 1/k, we can define k to be k is defined as log of 1/delta over epsilon square, where epsilon is our threshold on the error that we will tolerate, and then we don't want this to happen too often, so we bound it by delta. And so we consider the following setup, that we have a player. This player submits a query set to a system. Then the system provides the sketch to an estimator, and then the estimator will return the answers the query for the given for the submitted set. And for example, it could be the cardinality sketch. And the idea is that for these different efficient sketches that I mentioned, with high probability, they answer queries correctly. So they can answer exponential number of queries in K, correctly. And this is in the case that our inputs are not adaptive. Let's understand also like what I exactly mean by adaptive and non-adaptive. So non-adaptive setting is when I just submit queries, and then my queries, when I construct these queries, they don't depend on the previous answer. In the adaptive setting, we might use information from previous answers constructed. And so now we want to look at these questions that what kind of guarantees we can get if when inputs are adaptive. As I said, we will look at the setting that we will submit some queries, and this is in non-adaptive setting, but for the final query, we look at the answers for all these queries and then submit a new query. So we have one round of adaptiveness, or is this what we call a single batch version. This would be linear, so we can attack the estimator in linear size O of k, or if you are allowed to do adaptive queries, then in O of k squared, we can construct, we can violate the estimation error, but in this case, we put additional restriction on the responses, on the query response algorithm. So in terms of previous work in this line, for non-adaptive setting, as I said, there's exponential, and then for adaptive, there was the O tilde of k for when we use different randomness, or O tilde of k squared with differential robustness. For our work, we look at the known estimators such as mean hash or hyperlog log, or the ones that depend on the high priority k keys, and then we basically for the case that we have access to the optimal estimator, which basically tells us the exact gives us the estimate of the size. We give the single batch, and then in the adaptive setting, we look at a setting that we actually do omega of k rounds of batches of queries. And in this case, we actually assume that we have we are not going to get the size estimate, but we will have an response that would look something like this, that we have a soft threshold. So it will only tell us if the estimated size is larger than 2 times sum A, or if it's smaller. So it's only like binary information, 1 or 0. And if it's in between, it can be arbitrary and give us any answer. So for composable cardinality sketches, there is one basic idea that we have random priorities for our keys, and then when we are giving a set U, we will look at the k keys with the highest priority, and that would be our sketch, and then we answer the different queries such as cardinality using the sketch. The idea is that as our sets grow, we will contain higher priority keys, and so when we answer the cardinality sketch, then we say that this set is bigger. So then if we can identify these high priority keys and kind of gather them in a set, then we can fool the algorithm to give a response that to give a size, for example, estimate that is much bigger than the actual size. And now we use the composability because we can do this kind of approach that I first ask something about A, then I ask something about B, then if I identify the high priority keys from A or B, A and B, then I combine them and then construct this set for deceiving the estimate. Yeah, the idea is that we have this set U, we have the ground set U, then we find this set of set T of K keys with the high priority, that is the sketch of U. But then I construct a very small set, and that would have the same sketch as the set U. And then so the estimator would give us a wrong estimate in terms of the size. And then so now the question is how efficiently can we zoom on T and find this T? So as a warm-up, we can look at the following approach. I look at the ground set, I look at the random permutation of the items, and then I will make this, I will construct the set incrementally from x1 to xi, and then every time I look at the cardinality estimate of the set, and then every time the cardinality estimate goes up, I basically I record when this is happening. So now if I look at let's see I be the corresponding the size of the set the sketch sorry be the cardinality estimate of x1 through xi. Then if I look at c1 through to cn, in expectation in k log n places, I expect a jump for the change. And so now we can use O tilde of k queries to and then O tilde basically hides the log n portion. I make these queries, but I will construct this set, right? But then this was an adaptive approach because every time I use the answer. And so now this is kind of gives the idea of what our algorithm is for the optimal estimator. So what we will do is that we will have some sort of counter for each item. And then I will make O tilde of k queries. So every time we will sample each point with probability half, and then so we will have some set U. Then we will ask what is the cardinality estimate of this set U, and then we will increase the score by 1 over the estimated size. And then if we order, and then we repeat this 8 times. Then if we order the items by their score, the first k items would kind of reveal this, correspond to this high priority keys. This is the kind of experiments we did for this work. So let's focus on, say, the top bottom plot. So in this experiment, we look at the set of size 5,000. And then we look at the hyperlog plus plus with k equal to 100. And then what we will do is we look at attacks with a different number of queries. Meaning, so we look at attacks of 4 to the power of I queries. So this means that, let's say I have 256 queries. I will send 256 queries, then I will calculate my scores. Then I do the ordering by my scores. And then I will, then I have an order on these 5,000 items. Then if I start from here and look at all these sets, and then I look at the estimate of them, I will see that like if I actually so we, for example, look at this 256, so it's this plot. So if I order the items, so for 1,000, we kind of expect the, for a set of size 1,000, we kind of expect something written around 1,000. But then we can see that like we are violating this as we sort as we go by the scores. In the beginning, there is some memorization happening, so you can ignore that part, but you can see that like we kind of effectively identifying these high priority items. Or if we do something, so the plots on the top kind of show the reverse. So if we do the ordering in a reverse order. So we start with the lowest priority items and we start adding them. We are gonna underestimate the actual size. And then we do that for different sizes of K. So the idea is that then a set that we are given, so the algorithm has high priority keys. The cardinality estimate is slightly higher. So then we have, it's kind of like we have this bias that we will find toward the high priority items. And by repeating this enough times, we are able to kind of inject this bias and then kind of get a separation for the high priority keys and the lower priority keys. And so now let's move on to where we apply this to any composable sketches. And here we will have we will consider the setting that we actually gonna have a sub-threshold query. So we are not gonna get the exact size estimate, but rather we will get whether I have some size A, and then like we ask is the estimator will answer if the estimated size is larger than 2A or smaller than A, and in between can answer anything. And this is more specialized, but it can be approximated from the cardinality with the square with error, times error. So here it's kind of similar idea. It's just the amount of information we are getting kind of smaller, but we can show that like this is actually not going to cause problem, but we need to do more adaptive rounds. So we set A to be 1/16 fraction of the ground set size, and then this we have the probability Q for sampling each item. This Q is kind of linear in related to 1/16 times some constant, but it's we have to set it every round. And the idea is that we sample with this probability Q, and then we construct this mask that this mask is going to contain the high priority keys. And what will happen is that like we look at we always ask about the sketch of U union with the mask, and then we get the 0, 1 response. Then again we keep the scores that we update by this response C, and then when a score passes some median score threshold plus some constant, then we add it to the mask. And then the idea here is that like we find this mask that when it's added to any set U, a subset of ground set U, then the sketch of the mask and that set is kind of the same as the sketch of the ground set. And so, and then the proof idea is that basically the sketch is going to be dominated by the sum of K IID geometrically distributed variables, and then which will correspond to the number of times it will get to sample one Kn, and then we need to repeat this K times. So when our sum of our statistics is smaller than expectation, then what will happen is that the probability of responding 1 is higher, and then also a higher fraction of top priority keys will be included. So again, the idea is that the top priority keys, they will get higher scores on average. So some of them might get low score, but some of them will get high score. So then we will extract the high score and we will add them to our mask. But then we will update a queue, and then when we are determining queue, those high priority keys that were added to mask cannot affect queue or the sets that we sample anymore. So then there's a chance for the remaining top priority keys to. And this kind of wraps up the discussion or the ideas behind the K-squared adaptive query. And so some follow-up questions are whether any composable cardinality sketch should be based on prioritizing keys. And also another question is, what conditions do we need to design a robust sketch? For example, should we limit the number of times that each key is going to participate in the queries? So these are kind of related questions to our work, and they are the first one and the second one partially is going to be answered in the next talk. Thanks.
Great, questions for Sara? I think I have actually. So for your K-squared queries, is this K batches of like K rounds of adaptivity or
Yes, K rounds.
So if you wanted like a single round of adaptivity, is that possible? But with like K cube, like
single round with this kind of estimator and for any. No, I think we get the lower bound of K-squared as well, right from the TP work.
Don't have one. What's your framework kind of? I know you have some experience. Are there other algorithms people use in practice that are not based on prioritizing certain keys? I know.
Not prioritizing at all. I think so. The hyperlog is most widely used algorithm, and actually the plus one is like the version that is more efficient and it's most widely used. And this work is for, I think, most of the known sketches that I guess all of them are based on the main idea was that the slide that like we look at the highest priorities. In terms of whether there are, your question is
yeah, I guess are there other family algorithms that would be captured by this?
Yeah, I think like we need, we are just talking about the known sketches here. And those are also based on the priority. But the thing here is going to talk about some that are not based on priority.
Okay, all right, let's thank Sara again. It's good to meet you.